Hi, this is Schwartz from MasterMathMentor.com. This is video AB15. The topic is continuity and differentiability, and it covers the AB manual pages 70 through 73. Back in our pre-calculus days, and even early in this course, we dabbled in the concept of continuity. The informal definition of continuity is this. The curve is continuous if you can draw it without taking your pencil from the paper. This is a good loose definition, but not a formal one and not even quite accurate. For instance, we know the function while f of x equals x squared graphs a parabola, and we know the parabola is continuous. But can we really draw it in its entirety without taking our pencil from the paper? Try it. So we need a definition of continuity that is better than the one given above. So we will now use the following definition for continuity of a function. A function f is continuous at x is equal to c if all three conditions below hold. 1. The limit of f of x as x approaches c must exist. 2. F of c exists. And 3. The limit of f of x as x approaches c must equal f of c. What this really says is this. For the function to be continuous at some value of c, first, as x gets closer and closer to c, both from the left and the right, we approach some limit L1. Also, we must know that the function is defined at x is equal to c and is equal to L2. And finally, L1 must be the same as L2. If a function is continuous at all values of x in its domain, we then say it's a continuous function. A function can be continuous in certain sections of its domain and discontinuous at others. Problem 1 shows 8 graphs. Stop the video and for each graph, determine whether the graph is continuous at the point shown. And if it is not, decide which one of the reasons, 1, 2, or 3, for which the graph fails continuity. A is discontinuous at x is equal to 1 because the limit of f of x as x approaches 1 does not exist. This is sometimes called a step discontinuity. B is discontinuous at x is equal to 1 because f of 1 does not exist. The limit exists, but f of 1 does not exist. This is sometimes called a removable discontinuity, and we'll see the reason why when we see this in algebraic form. Number C is continuous at x is equal to 0. And D also is continuous at x is equal to 0. E is discontinuous at x is equal to 2 because the limit of f of x as x approaches 2 does not exist, and also f of 2 does not exist. F is discontinuous at x is equal to 2 because the limit of f of x as x approaches 2 does not exist. Be careful on G. G is continuous at x is equal to negative 2. There is a value to the right of the y-axis for which the function has a removable discontinuity. Finally, H is discontinuous at x is equal to negative 1 because the limit of f of x as x approaches negative 1 does not exist. In terms of continuity, when we examine functions, we could make the following conclusions. A, all polynomials are continuous for all values of x. B, fractions in the form of y equals f of x over g of x are discontinuous whenever g of x is equal to 0. It makes no difference if the g of x cancels out with the numerator. When it does, it creates a removable discontinuity. C, radicals in the form of y equals an odd root of f of x are continuous everywhere, while D, radicals in the form of y equals an even root of f of x are discontinuous wherever f of x is less than 0. Trig functions in the form of y equals sine of a of x, ax, or y equals cosine of ax are continuous everywhere. And finally, exponentials in the form of y equals a to the bx power are continuous everywhere. In problem 2, you are asked to find x values where there are points of discontinuity for these functions. Sometimes it is easier to express the answer in terms of where the function is continuous rather than where it is discontinuous. A, f of x equals negative 3x squared minus 5x plus 1 is a polynomial and thus continuous everywhere. B, f of x equals x squared minus 1 over x minus 1. The numerator would factor into x plus 1, x minus 1, and the x minus 1's cancel. Therefore, there is a removable discontinuity at x is equal to 1. This will graph the line y is equal to x plus 1, but with a hole at x is equal to 1. C, f of x equals the cube root of x squared plus 2x minus 4 involves an odd root and therefore continuous everywhere. D, f of x equals the square root of x squared minus x minus 6 actually involves a little work. The first step is to factor the polynomial, and we get f of x equals the square root of x minus 3 times x plus 2. For discontinuity, we are interested where this expression is less than 0. So the quantity x minus 3, quantity x plus 2 has to be less than 0. And it turns out that anywhere between negative 2 and 3, this expression will be negative. So the function is discontinuous on the interval negative 2 to 3. E, f of x equals the cosine of x minus 2 over x minus 2 is discontinuous at x is equal to 2. There is no removable discontinuity here because you cannot cancel. And finally, f of x equals e to the negative x minus 1 is 1 over e to the x minus 1. And e to any power is positive, and therefore this function is continuous everywhere. Problems 3 through 6 give piecewise functions. You are asked to determine whether the function is continuous at the transition point between the two sides of the piecewise function. You are also to justify your answer. Problem 3 is the piecewise function f of x equals x squared minus 3 if x is less than or equal to 1, and 1 minus x if x is greater than 1. To check out whether it's continuous, we look at the limit of f of x as x approaches 1 from the left, and we get 1 minus 3, which is negative 2. We look at the limit of f of x as x approaches 1 from the right, and we get 1 minus 1, which is 0. And since those two values are not the same, the limit of f of x as x approaches 1 does not exist, and therefore f of x is not continuous at x is equal to 1. Problem 4 gives f of x equals the piecewise function x squared plus 3x minus 2 if x is less than or equal to negative 2, and negative x squared if x is greater than negative 2. We first check out whether the limit exists. We look at the limit of f of x as x approaches negative 2 from the left, and we get 4 minus 6 minus 2, which is negative 4. We take a look at the limit of f of x as x approaches negative 2 from the right, and we get negative of negative 2 squared, which is also negative 4. Therefore, the limit of f of x as x approaches negative 2 is negative 4. F of negative 2 uses the top function and is negative 4. And since the values are the same, f of x is continuous at x is equal to negative 2. And since each piece is a polynomial, we could say that the function is continuous everywhere. In number 5, f of x equals 3 to the negative x if x is less than or equal to negative 1,
1 over x plus 1 if x is greater than negative 1. The limit of f of x as x approaches negative 1 from the left is 3 to the negative of negative 1, which is 3. The limit of f of x as x approaches negative 1 from the right is 1 over 0, which does not exist. And therefore the limit of f of x as x approaches negative 1 does not exist. Therefore f of x is not continuous at x is equal to negative 1. Number 6 reads f of x is equal to x minus 4 over x squared minus 16 if x is not equal to 4, and 1 over 3x minus 4 if x does equal 4. We start with the limit of f of x as x approaches 4. And we can factor x squared minus 16 to get x plus 4, x minus 4. And the x minus 4's cancel, so we're left with the limit of, as x approaches 4, of 1 over x plus 4, which is 1/8. F of 4 uses the bottom piece, which is 1 over 12 minus 4, which is also 1/8. So therefore, f of x is continuous at x is equal to 4. This is what is happening graphically. If we graph the top piece, x minus 4 over x squared minus 16, if x is not equal to 4, we get a curve with a removable discontinuity at x is equal to 4. The graph has a hole in it. But the bottom half of the piecewise function is a simple point. It is the point 4 1/8. So watch as the hole gets filled, making the function continuous. Problem 7 gives piecewise functions using the constant k. You're asked to find the value of k which makes these functions continuous. 7a gives f of x equals 3x plus 2 if x is less than or equal to 1, and 2k minus x if x is greater than 1. For continuity, we have to check out the limit. So the limit of f of x as x approaches 1 from the left is 5, while the limit of f of x as x approaches 1 from the right is 2k minus 1. For this function to be continuous, they must equal each other. So 2k minus 1 is equal to 5, and k is equal to 3. We see the result graphically. The blue curve and the red curve join up at the point 1, 5, and it is certainly continuous. 7b reads f of x equals kx squared if x is less than or equal to 2, kx minus 6 if x is greater than 2. For continuity, we look at the limit of f of x as x approaches 2 from the left, and we get 4k. And we look at the limit of f of x as x approaches 2 from the right, and we get 2k minus 6. Setting them equal to each other, we get 4k equals 2k minus 6, and k equals negative 3. Again, the graph is a good confirmation of continuity. Finally, in 7c, we have f of x equals k squared minus 12x if x is less than or equal to 1, kx if x is greater than 1. We check out continuity by looking at the limit of f of x as x approaches 1 from the left, and we get k squared minus 12. 1 from the right, and we get k. Setting them equal to each other, we get k squared minus 12 equals k. And bringing everything to one side and factoring, we get k plus 3, quantity k minus 4 is equal to 0, meaning that there are two possible values of k, negative 3 and 4. We graphed both of them and showed that they are both continuous at x is equal to 1. Suppose a train was traveling along a straight track at 30 miles an hour and needed to move into a curve. The track plan is shown on the screen. What do you think would happen when the train transitioned from the blue to the red? Now let's modify the track plan to the one below. What do you think would happen now? The train traveling the track above would most likely derail. while the train traveling the track below would most likely stay on the track easily. Why? The reason is that the transition in the lower curve is a smooth one. In calculus, we're interested in examining whether functions are differentiable. In simple terms, a function that is differentiable is smooth. A differentiable curve will have no sharp points in it, or points where the tangent line to the curve is vertical. If a train were traveling along a set of tracks that are differentiable, at all locations the train will stay on the track. Steel roller coaster tracks are differentiable, and that's why your ride is a smooth one, while wooden roller coaster rides tend to be herky-jerky. That's because at various locations on the track is not completely smooth, intentionally so.
There are some definition and rules that we need to understand about differentiability. First, differentiability at a point. A function f of x is differentiable at x is equal to c if and only if f prime of c exists. This means that in order to prove that a function is differentiable at some point, we have to look to determine whether its derivative exists at that point. That is how we prove differentiability. Differentiability on an interval. A function f of x is differentiable on an interval AB if and only if f prime of c exists for every value of c in the interval AB. So in order to prove that a function is differentiable on some interval, you have to be sure that for every value in that interval, the function is differentiable. A differentiable function. A function f of x is differentiable if and only if f prime of c exists for every value of x equals c in its domain. Polynomials, the sine and cosine function, and exponential functions are differentiable functions. Here are the rules that describes how continuity and differentiability are related. First, if a function f of x is differentiable at x is equal to c, then it must be continuous at x is equal to c. Remember, D, then C. Think of Washington, D.C. Second, if a function f of x is continuous at x is equal to c, then it is not necessarily differentiable at x is equal to c. We will see examples of that coming up. Third, if a function f of x is not continuous at x is equal to c, then it cannot be differentiable at x is equal to c. This makes total sense. If you are unfortunately on a roller coaster whose track is not continuous at some point, then certainly it cannot be smooth at that point. Let's examine three continuous curves at x is equal to 1. The green curve hits a relative maximum at x is equal to 1, which means its tangent line is horizontal, which means the slope of the tangent line is 0, and thus this is a differentiable curve. The two red curves also hit a relative maximum at x is equal to 1. However, this is called a cusp point because the tangent line is vertical. It is also not differentiable at x is equal to 1. The blue curve hits a corner at x is equal to 1 because it is formed by straight lines and not curves. There is no tangent line at x is equal to 1, and thus it is not differentiable. This is all in line with what was on the previous sections. Smooth curves are differentiable. Curves that hit a sharp
point are not. Watch what happens when we put all curves on the same screen and zoom into the point 1, 4. We now see the graph in the window with x running from 0.98 to 1.03 and y running from 3.95 to 4.03. The green curve is now almost a straight line. This happens because of local linearity. However, the cusp point curve has now gained a sharper cusp point. Obviously, it is still not differentiable. And notice that the corner has not changed. No matter how much we zoom into the corner, it still remains a corner. Here is the procedure to determine whether a function is differentiable at x is equal to c. You will use your limit procedures to check continuity at x is equal to c. Your results will either be that the function is not continuous or continuous. If the function is not continuous at x is equal to c, then it's not differentiable at x is equal to c, and you can stop. However, if the function is continuous at x is equal to c, then you're going to have to check differentiability. You take the derivative and determine whether the derivative exists at x is equal to c. If it does, then the function is differentiable at x is equal to c. If not, it is not differentiable at x is equal to c. Just as the transition in a railroad track from straight to curved must be a smooth one, the same is true with piecewise functions. Usually both pieces of the piecewise functions are differentiable. However, we want to check differentiability at the point when the rule changes. For the following 4 problems, you are given piecewise functions and you are to check continuity and thus differentiability at those points. A reads f of x equals x squared minus 6x plus 10 if x is less than or equal to 2, and 4 minus x if x is greater than 2. First thing we check is continuity, and we look at the limit of f of x as x approaches 2 from the left and 2 from the right, and they are both 2, so this is a continuous function. We now check out differentiability by taking the derivative of both sides. And we get 2x minus 6 if x is less than or equal to 2, negative 1 if x is greater than 2. And now we look at the limit of f prime of x as x approaches 2 from the left and 2 from the right. From the left, it's negative 2. From the right, it's negative 1. They're not the same, so this is a continuous function but not differentiable. We can see that in the graph. At 2, the slopes are different. It's not a smooth transition. B reads f of x equals x squared plus x minus 3 if x is less than or equal to negative 1, negative x minus 4 if x is greater than negative 1. We first look at the limit of f of x as x approaches negative 1 from the left and right. They are both negative 3, and therefore this is a continuous function. We look at the derivative, which is 2x plus 1 if x is less than or equal to negative 1 if x is greater than negative 1. And now look at the limits. The limit of f prime of x as x approaches negative 1 from the left is negative 1, and negative 1 from the right is negative 1. These are both the same, so this is a continuous and differentiable function. If you look at the graph, you will see that the transition from the parabola to the line is smooth. C reads f of x equals 2 minus the cube root of x minus 4 if x is less than or equal to 4, and the square root of x plus 5 if x is greater than 4. We first look at the limit of f of x as x approaches 4 from the left, and we get 2, 4 from the right, and we get 3. Therefore, the limit of f of x as x approaches 4 does not exist. That makes this function not continuous, and therefore it is also not differentiable. D reads f of x equals x minus 3x squared if x is less than or equal to 0, and sine of x if x is greater than 0. Even though we are looking at a parabola and a trig function, it is possible that it can be differentiable at the transition point. We first look at the limit of f of x as x approaches 0 from the left and get 0, 0 from the right and get 0, and therefore the limit of f of x as x approaches 0 is 0. Our first derivative is 1 minus 6x if x is less than or equal to 0, cosine of x if x is greater than 0. And now we take a look at the limit of f prime of x as x approaches 0 from the left, which is 1, 0 from the right, which is 1, and therefore the limit of f prime of x as x approaches 0 is 1. That makes this function both continuous and differentiable. And that is clear on the graph where the transition between blue and red at x equals 0 is a smooth one. One final point. These problems are the types that you will see on the AP exam. It is not enough to just understand the concepts. You must be able to write them and with proper notation. If you cannot explain your reasoning using the proper and accepted methods, you are not going to do well on the AP exam. So practice writing these the way they should be, with limit notations and clear statements. In 9, you are given piecewise functions in terms of the constants a and b. Your job is to find the values of a and b that make both functions differentiable. 9a reads f of x equals ax squared plus 1 if x is less than or equal to 1, bx minus 3 if x is greater than 1. For this function to be differentiable, it first must be continuous. So we look at the limit of f of x as x approaches 1 from the left and get a plus 1. And the limit of f of x as x approaches 1 from the right, and that gives b minus 3. These two must equal each other, so a is equal to b minus 4. Any values of a and b such that a equals b minus 4 gives a continuous graph. For instance, we see a graph with a equals negative 2 and b equals 2. So there are an infinite number of continuous graphs. But we want differentiability as well. So we look at f prime of x, which is 2ax if x is less than or equal to 1, b if x is greater than 1. And we look at the left-hand limit and get 2a, and the right-hand limit and we get b. So b has to equal 2a. So we have two simultaneous equations in two unknowns. A equals b minus 4 and 2a equals b. To solve them, we will say that a is equal to 2a minus 4, and that makes a equal to 4, and therefore b is equal to 2 times 4, which is 8. And we see the graph in confirmation. 9b reads f of x equals ax cubed plus 1 if x is less than or equal to 2, and b quantity x minus 3 squared plus 10 if x is greater than 2. Our first job is for continuity. So the limit of f of x as x approaches 2 from the left is 8a plus 1. 2 from the right is b plus 10. Setting them equal to each other, we get b equals 8a minus 9. So any values of a and b such that b equals 8a minus 9 makes this a continuous function. For instance, if a equals 1 and b equals -1, we see the function which is definitely continuous but clearly not differentiable. So for differentiability, we look at f prime of x, which is 3ax squared, if x is less than or equal to 2, 2b quantity x minus 3 if x is greater than 2. So the limit of f prime of x as x approaches 2 from the left is 12a, and 2 from the right is negative 2b. Setting them equal to each other, we get b equals negative 6a. We now set 8a minus 9 equal to negative 6a and get a equals 9/14. Therefore, b equals negative 6 times 9/14 or negative 27/7. The graph is certainly a good confirmation of differentiability at x is equal to 2.